Hello, let's start with the second part. So you probably have here about a complex power is something like a beer, like the beer itself is the active power and foam is the reactive power. You probably have listened to those kind of similes, but this does truly doesn't give you very well understanding of what is reactive power. In this part, I will try to explain you what is reactive power, what is active power, what is complex power, what is instantaneous power. So let's start with instantaneous power. Well, if we have, let's assume that we have what is called two ports system. So we have a connection in these 2 points, and inside of this gray box there is something we don't know. But we know that we can measure current I and voltage V. So both of them, they are a function on T. So no matter what is the signal, so the power that is actually going to the gray box, it will be P. This is multiplication of V times I. So this is something very clear for everyone. So let's assume that, well, we have sinusoidal waves for both of them. For the voltage is representing like this first one. Now I will make some different. I will call theta V, like the phase angle related with this voltage. This is the signal of the voltage. Well, this one, which is dependent on T. And below I have the current. So it's a sinusoidal wave. And the important thing is like the phase angle is theta I. Well, no matter what is those values, so we can just multiply P, what is the instantaneous power, the function P and T, will be the multiplication of these two functions. Oh, okay, it's a little bit tedious multiplying these cosines and then computing what is the equivalent, but I'm going to do this for you. Yes, I'm assuming also like the frequency of this gray system is omega. Typically is this 50 Hz or 60 Hz of the power grid. So if I multiply these two sinusoidal waves, I will have another sinusoidal wave, which is this blue one. This is P, which is a scale, of course, this B times I. But there is something very interesting here, like, well, for some moments, this P is negative. What is the mean of that? Like, well, for some moments, the gray box is actually sending back to whatever is the source. Let me call here, this is the source of power, sending back this power. The same if for some moments, so this is positive, means like power is going to the gray box. This is very different for what we understood from the DC circuits, because now power, instantaneous power, can go from positive to negative. Yeah, mainly it's positive, but also it's negative. So if we integrate over some period, it will be positive. It means like in average, so there is a delivery of power to this gray system. Another interesting thing here is like, well, we can see like the frequency of this power is double. I will do this multiplication for you, and then I will arrange terms in such a way like I'm quite interested in the way that I will arrange these terms. So you can see like if I'm multiplying this B times I, right? B times I. So I will have this definition that I have here. Well, I can observe that there is some terms which is repeating here, this one and this one. Okay, and this term basically doesn't depend on time, so it will be always constant. So there's this term is that, so this guy doesn't depend on the time, so it depends only on the phase angles and depends on the magnitude of the amplitude of the sinusoidal wave. So this is a constant number. So this is also the same thing, but it's multiplied by cos of 2 omega t, right? So if I'm integrating this value over time, so if integration over some t0 to t0 plus t, so the integration will be give you 0. And we have also another term here, the last one, which is similar to them, but it's a sign. And they also, if multiply, it's multiplying some signs of 2 times omega t. So the integration over the time will be giving you 0. So it means like if I'm integrating the power along the time, so it will give you some typically positive value for this case if p and I are positive. Also depends on this difference, right? And so this is what is typically called active power, because this is the power that we are going to deliver in average. Also, what we have here, this part, which is important because this is all this power actually, if we go to the time domain, we see like this is power that's going forward and backward. So this term, it is called the reactive power. Yeah, by definition. So we are going to call this term, this pink one, reactive power. So here we have the active power. Real power, active power, sometimes also called average power, because this is the average power that we have. So average power is equivalent to is measuring in watts, and reactive power is measuring volt-ampere reactive, right? So we have volts and we have amperes, and these have no units. So we know, like by definition, this reactive power is a part of the instantaneous power. So let's go into detail of these 3 elements that I mentioned before. We have 3 elements that represents most of the possible passive load that we can observe. Remember, in a purely receptive circuits, both of them were in phase, means like the phase angle of B and phase angle of I are the same, right? So it means like if I go back, I'm replacing here in instantaneous power. So what I'm going to have is like, well, P, instantaneous power, will be this active or average power P, capital P, yeah, then these 2 times cos of omega t. So we can represent here, like we see this looks like a sinusoidal wave as well, but the frequency of this sinusoidal wave is the double of the voltage and the current. So it's going to 2 times omega. And also it's always positive, so there is no negative. Means like resistive elements are not providing any kind of power back to the source. Now let's go to the case of inductive elements. And remember, like current was lagging the voltage by 90 degrees in a perfectly inductive circuit. So what does mean of that? So it means like the difference of theta I, like this phase angle of I, will be whatever is the phase angle of voltage minus 90 degrees. So if we are replacing this in instantaneous power formula, so we are going to have this value, right? So we see here like there is not average power. So this is very important remark. If I have not inductive, if I have an purely inductive element, there is not active power that can be consumed in this inductive element. So it will never consume any power or average power. But there is another, what is called reactive power, this Q, which is basically power that go forward and backward. So it's in average will be 0, these typically have magnetic fields. I have here a magnetic field, and typically what happens is like when the voltage, when powers, when the current goes through this inductor, so it creates a magnetic field, and this magnetic field actually accumulates some energy that which is discharged when the voltage, when the current can change the sign, right? And this is some energy that go forward and backward. We have something similar for the capacitors. In the capacitor, we have a current is actually leading the voltage, so it means like phase voltage plus 90 degrees will be equal to this phase angle of the current. So we observe here like the Q is a negative value in general, so just by replacing those values. So we have something similar interpretation for this case where the capacitor are actually accumulating or storing this energy in some electric field. When the current signal actually are in some positive or negative, so it's charging, and the other part will be discharged, right? So that's basically the instantaneous power is a power that is oscillating between some positive value and negative value, but in average it's zero. So again, means like a capacitor, if this is ideal, is not consuming any energy. So let's go a little bit more into this average power. Well, let's assume that we have some resistor or resistance, and we have a sinusoidal source of generation. What will be this effective value that will replace a DC load? So if I'm replacing a DC load, which is always constant, what will be this equivalent power? Well, we can actually determine this by using this average power delivered by the resistor. So this is the integral in one period, 1 over t, going from t0 to t0 plus capital T. So if we solve that, so we see, yes, we are replacing here. This is a BRMS, so root mean square to the square. So that actually is the active power will be B squared divided by R. And if you remember, in DC, this looks like pretty much of one of these formula that give you the power that which is consuming a resistor. So this BR square root mean square is basically this effective value. Sometimes it's also called effective value, which is this root mean square value. Okay, then let me give you another definition. Remember, like the instantaneous power was composed by several terms, 3 terms, in the way that I arranged them. And there was something that I called capital P, and the other part I called capital Q, and I called them average power and reactive power. So I will actually come up with an intention, and we call complex power, to the composition of these two elements. So I will say like, well, P will be representing some real value of some complex number, and Q, this reactive power, will represent the imaginary part. And this complex number actually is what I call complex power. And I will show you like, well, this is convenience for me. It's actually, it's not something very easy to grasp from the physical meaning of what is going on in the power system, but for convenience I'm creating this complex number. Right, so if I'm measuring this power in watts, and remember this is volti-amperes reactives, so the complex power is measured in volti-amperes. And I have something very interesting here, right? Well, this is a complex number, so I can basically represent this complex number in the complex plane. So this is the real part, this is the imaginary part, so this is what is how looks like this complex number. And of course, so this have some module which is called apparent power. This is the module of this complex number, and there is a angle associated with this complex number. So we are using this Euler identity, and we can get like this angle basically will be the arctan of this q divided by p. So because I have a expression for q, I have expression for p, so I can just replace them, and I will see, well, this is the tangent of the phase angles of the voltage and current. So in somehow this complex power and this angle actually is related almost in direct way with the difference of phase angles of voltage and currents. This difference is called power factor angle, but the cos of phi is what is called power factor. And you can imagine like this cos phi of this difference, it's what is giving you what is the active power. Okay, here is a question about what are the preferred values of power factor. Well, typically those values that give you the maximum active power or average power. Why? Because this is basically the power that we can use for make work. The reactive power is in there, and we cannot escape from that because it's part of the instantaneous power. Depends on if you have a more inductive or conductive circuit, but it's in there. And the active power is the one that we can use for doing work. And this is basically, if you think about the energy that you are paying at your home, so basically you pay for active power. So let me work a little bit more about with this complex number, what I call complex power. So this I'm replacing now here the value of the active power or average power, and this is the value of Q, right? So I'm working here with those values, so I'm moving things around, and then I'm using this Euler identity. So I see here like I can have an expression that say, well, this complex power is 1/2 of the voltage phasor times the current phasor conjugate. So this y star is a conjugate number. Remember what is a conjugate number? Conjugate numbers, if you have a complex number a time with an angle theta, so it's let me put this bold phase, right? So this conjugate will be the same value with minus theta. Okay, then we can continue just working with the effective value or the RMS value, and we are replacing that, so we have even some nicer approach. Like this complex power is voltage time current. This is very similar to what we have in DC, but of course with a special feature that they are complex numbers. They are not representing the amplitude, but they are representing the effective value. So let me summarize this and in this part, like what we have on direct DC, what we are now using for AC. So remember, this is the Ohm's law. We have something very similar to the AC, which basically the voltage is a linear function of the current. And in DC, in continuous, we have that the power is voltage times Y. In AC, we have something a bit more different, and we have this complex power, which is defined with the 1/2 times the B times I. This is the two complex numbers, or equivalent, we can say like this complex power is equal to this effective voltage phasor times the effective voltage phasor of the conjugate of the current. And those are actually pretty similar. So let me go through an example how we can apply that. So given the voltage and current of at one point, just calculate what is complex power, active power, and reactive power. So I have this signal of voltage, which is 100 cos of omega t times plus 15 degrees, which is measuring voltage. And I have this current, which is measuring amperes. Right? So the first thing that I'm going to calculate what is complex power first. So the first thing that I'm going to do is like, well, I'm going to transform these two phasors. So the phasor of the first signal is 100, and this is kind of straightforward, and the angle is 15 degrees. The phasor of the current signal is equal to the 4, and the phase angle, so we have minus 15, so this will be minus 105. So then I can compute what is the complex power. So the complex power, remember, was 1/2 of V I start. So it is equal to 1/2 of 100, 15 degrees, times 4 minus 105 degrees. Okay, if you word, this is pretty simple. So we have, yes, we have 1/2 times 100, this is 50, times 4, this is 200. Yes, and we have 15 degrees minus 105, so we have 120. Okay, that's all. So I have already complex power. This is a complex number. I can also transform this complex number in polar form into complex number in rectangular form. So if I'm using my calculator for transforming that. This is 100 plus J 173.1, and this is measuring volt amperes, right? So the answer to the last two questions, what is the active power? Active power is minus 100, and what is the reactive power? So reactive power is 173. Let's assume like we have a system where it have an equivalent impedance C, and I'm giving you the equivalent phasor for the effective current. So this effective phasor is representing the sinusoidal wave with the effective values, and also giving you what is the effective voltage phasor. So if you remember, so this is the equivalence Ohm's law, and we can compute by replacing this function into these formulas of the complex power. So we can compute what is the active and reactive power just in terms of currents. So basically I'm replacing this voltage by this expression, and then I can get P and Q. So you can do at home. This is a nice exercise. But the important thing here is like, well, if you're replacing that, you see like, well, the active power will be a function of, this is the one half of the current to the square. This is the amplitude of this signal, whatever is the signal, to the square. So this will be always positive times R. So it means like this active power depends on to the square of the current. Below also we have like the reactive power, so depends to the square of the currents. So what is the mean of that? Like, well, you probably know, like, if you have very high currents, so and for a line which is not ideal, so it means like have some losses, so you will have very high high current, you will have high losses or high power, which is lost in with these resistive elements. But then you see like, well, in similar way, this is connected current with the reactive power. And means like if you have high reactive power, so implies that you will have high currents. And somehow, if you want to design systems that you want to deliver power from one point to another, and you probably prefer to deliver only active power, because this is the power that you are going to get paid, and this is the power that makes some work. But the reactive power also can be delivered, but if you're delivering, so you are increasing the current that is needed to go through this line, and also it's increasing the amount of losses, because yes, the current increases and then the active power also increases. So it means like, well, if I can design in somehow my system, I will prefer to have reactive power produced locally. So let me go to our final example. So let's imagine that you have two sources of voltage. So V1, which is 120 minus 5 volts, and then you have the other one, you have 100 volts, and they are connected by a source line of impedance, which is this value given here. So the problem say, well, determine what is the real and reactive power supplied and received by each source and the loss of the line. So this is a little bit strange for us, because we say, well, this is a generation. Let me call this is source 1. And that is connected with another source. It's quite strange, right? So this one actually have 120 minus 5 volts, and this one have 100 volts. The intuition says like the one who have higher voltage should be the source of power, so it's sending power from 1 to 2, right? I forgot to include here the impedance. So here we have this 1 J7. Okay, so I want to compute what is the real and reactive power supply or receive at each end, and what is the power loss in this line. So in this case, I will use my computer, and then I will use complex numbers. So first of all, this is done by Julia, and well, you can see here is pretty similar to MATLAB. So you can see here like, well, first one, so voltage in one is 120. Let me copy this in. I will keep here. Yes. So voltage in one is 100, and then I am expressing like exponential of this J times of, well, remember you have to use radians. So this guys, this function actually is transforming degrees to radians. So basically just defining phasor B1, phasor B2, and this is C. Just definition of a complex number. So in Julia, for an imaginary number, so you just use IM. Then the currents, so you can state like, well, what is the current that goes, current that go from I from 1 to 2. Well, this current will be B1 minus B2 divided by C. Yeah, because it's how much voltage drop from here to here, which is B1 minus B2. We have something similar, but for the current that go from 2 to 1 will be B2 minus B1 divided by C. So this is these two other equations that I have here in this side. So I can compute B1 and B2. And now I can just finally compute what is the power that is sent from S1 to 2, which is the compressed power that I'm sending from 1 to 2. And then what is the power that I'm sending from 2 to 1. Well, you can imagine these two powers are not the same. They are not differing only in the sign because there are some losses in between by this element in here. Yeah, so well, they are representing here. I will give you the detail, but you can see here like one is positive, one is negative. And losses at the end is a balance, right? So I say like, well, the summation of S1 plus S21, this will be the losses, whatever is that. If both of they are summing zeros, it means like there are no losses. And well, the last lines are representing some prints just to represent values. Also in degrees, because I like to read degrees instead of radians. So here are the values. Let me put here again the system, and then I will make some zoom to look at here. So voltage are just, this is what we have as B1 and B2. This is just information that I have. And then this is some computation, current from 1 to 2 and current from 2 to 1. Still for me it's not clear because these values for both currents, this one and this one is positive, but well, the phase angle is different. But the important thing here is like I want to see this active power. So who is sending power to whom? And you see like S12 is negative. It means it's receiving power, and S21 is positive, so it means like, well, power goes from 2 to 1. And this is very strange, right? If you think about why a system like this, where this voltage here is lower than this other voltage, why this source 2 can actually send energy to the source number 1. And the key, and this is important, is not only in the value of the magnitude, but also is in the phase angle. So it depends on what is those phase angles, and actually is giving you the insights of where this energy is sending, which is the direction that the energy is sending from 2, right? And typically goes from larger phase angles to lower phase angle. This is -5. So if you see 0 is rather than -5, so that is typically the way that we find. So this is very interesting fact that we are not used to understand, because in DC it doesn't happen. So we know always like the power goes from the higher voltage to the lower voltage. And of course, so you can see like currents actually, it's a sinusoidal wave. So it's going from 1 to 2 and from 2 to 1. Both of them, they are positive, then negative. In average is 0. But the power, the average power actually is going from 2 to 1. So of course, you can see like from 53 to 44, there is a difference. So this difference actually is lost in this element of the transmission line, so which is represent the transmission line.